Okay, so this video is on how to name binary ionic compounds. So there are specific rules for how to give the name and formula of a compound depending on what type of compound it is. So the first thing that you need to do when you see a compound is identify whether it is ionic or covalent, or if it has a special circumstance involved in the compound. And later on, you'll see what I mean by that. So the first one that we're going to talk about is binary ionic, and you're going to identify this by a metal and a non-metal. So the word binary just means that there are two atoms in that compound. That prefix bi means two, so binary ionic means I would only have two atoms in the compound, one being a metal and one being a non-metal. So if you identify the compound that way, then these are the rules that you will use to name it. So the cation is always written first, just as its name appears on the periodic table. The anion name is written next, but you keep the root of what you see on the periodic table for its name. Keep the root, but then change the ending of that element's name to IDE. So for example, if I have the compound Al2O3 written as a chemical formula, and I ask you to give me the name of that compound, you would look up Al on the periodic table and find it. And because it is the metal, it's the cation, we just name it exactly as it appears on the periodic table. So we just write aluminum, and that's the cation. It comes first. So then O on the periodic table is oxygen. So we'll keep the root, or kind of what identifies it as oxygen, which is just the OX. And instead of keeping oxygen, we change it to oxide. So it always ends in IDE. So by itself, it's oxygen, but in a compound, we change that to oxide. So that the name of this ionic compound would be aluminum oxide. Okay, so going from the name and writing a chemical formula, this should be a review. We've covered this before, but to find the chemical formula for a binary ionic compound, you get the charges of each atom involved and then crisscross them, as we said. So we think about this as just switching the charge to become the subscript of the other atom. So in this first example, I have calcium and iodine that are bonding. Calcium is a metal, iodine is a nonmetal, so this is ionic. Calcium has a charge of +2, and iodine has a charge of -1. I know that from the oxidation state trend on the periodic table that we have talked about. So then when you switch them, the charge of calcium 2 becomes the subscript of iodine. So this 2 is no longer representing a charge when you cross it down. It's representing the number of iodine atoms that are needed in this compound. So I need 2 iodine atoms. Then the 1 from iodine does cross down to calcium to become calcium subscript, but we just don't have to put a subscript of 1. We can just leave it as Ca. So that's how you get the formula, and then we would name it calcium iodide, changing iodine to iodide. The next example, barium and sulfur bonding. Barium has a charge of +2, sulfur has a charge of -2. So this is one of those situations where the charges cancel each other out. So having 1 barium and 1 sulfur is a neutral compound, so we would reduce those charges of 2 down to 1 and just get BAS, which would be barium sulfide. So these are just some examples that I have in the PowerPoint, and so I would suggest that you go through and just work some of these examples in the PowerPoint and practice, test yourself to make sure that you are getting the same answers that I have here in the PowerPoint. Okay, so now we have a special situation of binary ionic where we're bringing in the transition metals tin and lead. So any binary ionic compound that contains or that starts with a transition metal or the elements tin or lead, those compounds then have to use the stock system of naming. And so that's how you're going to identify when you need to use the stock system. So that's just identification, seeing a transition metal and adding to that tin and lead are some exceptions. Even though they're not transition metals, they still require the stock system of naming, so you just have to memorize that they are exceptions. Okay, so what is the stock system and why do we have to use it? So referring back to that trend on the periodic table for charge or oxidation state, every time that we talked about that trend, we skipped the transition metal family, the D block, because we said they just do not follow the trend. So the reason for that is that these elements can form different charges. So they are still metals and they're going to become cations, but they can form multiple different charges. So to distinguish which ion is involved in a certain compound, we use what's called the stock system. So the rules for the stock system, we're just adding a little bit onto the rules that we just did for normal binary ionic, but this time we have to add a Roman numeral right after the metal's name to tell which charge is being used in that particular compound. And then the anion name would follow as usual, where you change the ending to IDE. So just to give you a visual of what this looks like, these are just 5 common elements that we use for the stock system. So chromium can actually have a +2 or a +3 charge. So if chromium with a +2 charge was forming a compound, I would call it chromium 2 and then whatever anion it's bonding with. And then if it was chromium with a +3 charge, we would name it chromium 3. So the Roman numeral represents the charge of the cation, because the cation is the one that can have multiple charges. The anion, all of your anions can only form that one charge. So the negative ones will never need a Roman numeral, only the positive ones. So here are some examples. So first we're going to practice starting with the name and getting the chemical formula. So if I have copper 2 chloride, I look up copper on the periodic table. Copper is a metal. Chloride, which came from chlorine. Chlorine is a nonmetal. So I've got metal, nonmetal. So I know this is ionic. And ionic requires charges in order to figure out what the formula is. So looking at copper, it is in that transition metal family. So I don't know what its charge is going to be. That's why this Roman numeral 2 is here in parentheses. It is telling me copper's charge. Chlorine, I know from that trend that chlorine's charge is always -1. So again, this 2 in Roman numerals tells me copper's charge, and the -1 for chlorine I got from the periodic table. So now, just like normal, I'm going to take those charges and switch them, cross them down, and make them the subscripts So the charge of 2 from copper crosses down and becomes chlorine's subscript. And then chlorine's charge of 1 crosses down, switches over, and becomes the subscript for copper. So that would be your final answer because we cannot reduce it. And then just to compare, this next example is copper 1 chloride. So the only difference is we've gone from copper 2 to copper 1, and they're both bonding with chlorine. So again, this Roman numeral tells me the charge of copper. And now that I have the charge of both, I'm going to cross them down and get the final chemical formula. So you get a different formula depending on what Roman numeral or what cation is in your compound. Okay, so this part is a little bit trickier when you start with the formula and go back to the name. So Cr is the element chromium. It is in the transition metal family. So it's a metal. Bromine is a nonmetal. So this is an ionic compound. And because chromium is a transition metal, I know I have to have a Roman numeral right after chromium's name, telling what chromium's charge is in this particular compound. So chromium can have multiple charges, but I want to know what is chromium's charge in this compound CrBr2. So to form or to get the subscripts that we have here, a 1 and a 2, those came from the charges that these elements have. And those charges were crossed down to become these subscripts. So what we're going to do is uncross them. So this subscript of 2 on bromine, I'm going to uncross it, send it back over to chromium. And then there's a 1 for chromium that I'm going to send back over to bromine. So we're going to uncross them. And so you would get this if you uncross. Again, the 2 from bromine goes back to chromium. So that's where I got 2 here. The 1 goes back to bromine. That's how I got a 1 here. So after you do that, you always have to check your anion charge to see, is this the actual charge of bromine that we know from the periodic table, or has this compound been reduced down to simplest term? And if we look, -1 is the correct charge of bromine. So in that situation, when we uncross and get the correct anion charge, then that means we have the correct cation charge as well. So we can go ahead and make the cation's charge the Roman numeral in the name. So the answer would be chromium 2 bromide. So again, this 2 comes from, or this Roman numeral 2 comes from the charge of chromium. Okay, another example, Fe2O3. So iron is a transition metal, oxygen is a nonmetal. This is an ionic compound. So I'm going to uncross to get the charges. So the 3 from oxygen went back to iron to become its charge, and the 2 from iron went back over to oxygen. So I uncross them. Then the next step is to always check the charge of the anion. Is this the correct charge for oxygen? And yes, again, this is the correct charge. If I look up on the periodic table, oxygen always has a charge of -2. So because it is the correct charge for oxygen, then this is the correct charge for iron as well. And so that charge for the cation becomes the Roman numeral. So it's iron 3 oxide. So you might be wondering, what do I do if I check the anion charge and it's incorrect? So let's look at one of those examples. If I have FeO, there are no subscripts, so that would mean that iron has a +1 and oxygen has a -1. but we just did an example with oxygen, and we just talked about how oxygen always has a -2 charge. So that means that we need to multiply by 2 for both, because you can't just do it for one. We would have to multiply both of these charges by 2 to get to oxygen's correct charge of -2. So if I multiply each one by 2, here's my +1 and my -1, I'm going to multiply them by 2 because I need oxygen to have its correct charge. So doing that would get iron up to +2 and oxygen to -2. Now that it's correct, the charge of the cation can become the Roman numeral in my name. So I would get iron 2 oxide. So this 1 was incorrect. This +1 for iron was incorrect because the -1 was incorrect for oxygen. So we had to figure out what it was before those charges or subscripts were reduced. So sometimes it can be confusing and easy to make a mistake in this process. So I would highly recommend whenever you get an answer like iron 2 oxide to check it, just like I did down here in this box. So iron 2 oxide is my answer. So let's just pretend that I'm starting here and going back to the formula. So this Roman numeral represents iron's charge of +2, and oxygen, I know, always has a -2. So so far, when you've been writing formulas for ionic compounds, you may see right at this point, +2 and -2, that those are going to cancel out and neutralize each other. So the final chemical formula would just be FeO. Or maybe you like to go ahead and cross down the 2's. So each atom, both iron and oxygen, would get a subscript of 2 when those are crossed down. So in that case, you would still have to reduce it, right? You either reduce it here when it's the charges or reduce it here when they are subscripts. Either way, you get down to the final answer of FeO, which is the same chemical formula that we started with up here at the top, FeO. So that's just a way to check yourself and make sure that you've gotten the correct answer. So let's look at one more example, PbS2. So again, we're going to uncross. This 2 from the sulfur is going to go back up to Pb, or lead. So it goes back up and becomes the charge of lead. There's really a 1 here on lead's subscript, so it crosses back over to sulfur and becomes sulfur's charge of -1. So then the next step is always to check the charge of the anion. Remember, anion charges can never change. They can only have one specific charge. So when we look at this, when we look at sulfur on the periodic table and look at that trend, we know that this is not the correct charge for sulfur. Sulfur is always -2. So to get from -1 to -2, we need to multiply by 2, and you have to do both charges. So this +2 and -1, when we multiply by 2, are going to become +4 and -2. So doing that, just multiplying instead of the reverse process where we reduce the charges down, now we're multiplying to get back to the beginning. So after multiplying, lead has a +4 charge, sulfur has -2, and this is the correct charge for sulfur, so this is the correct charge for lead, and so we can call it lead 4 sulfide, coming from lead's correct charge. And I know it's correct because it goes with sulfur's correct charge. So yes, side note, this is the Roman numeral 4, so you may want to take a moment and memorize that. We shouldn't really go above 4 for our Roman numerals. So if you know 1 through 4, you'll be good to go. So then we can quickly check our answer, lead 4 sulfide, down here. So the 4 in Roman numerals tells me lead's charge. From the periodic table, I know sulfur's charge is always -2. You can reduce this 2 and 4 now, or you can go ahead and cross them. So the charge of sulfur would cross over to become lead's subscript. The charge of lead, which is +4, would cross over to become sulfur's subscript. And then a 2 and 4, we can definitely simplify that by dividing by 2. And so we would get PbS2. And that is the correct answer because it is what we started with in the very beginning. So this bottom part is just to double check that the name that we got matches the chemical formula that we started with. Okay, and so then I also have some additional problems in the PowerPoint. So again, I would highly suggest going through and seeing if you can come to answer these questions correctly and where you have some correct answers to compare to. All right, this has been binary ionic naming, both with and without the stock system. Thanks for watching.